Good morning, everyone. I welcome you all in the first online refresher course in the chemistry hosted by Department of Chemistry, Gujarat University, Ahmedabad.
Good day, everyone. I, Dr. Hitesh M. Parekh, thank UGC MMTTC of Gujarat University for giving me an opportunity to connect with you and deliver my session on basics of supramolecular chemistry. I thank Professor Dr. Jagdish Joshi, Professor and Director of UGC MMTTC, and Dr. Dilip Vasawa, Course Coordinator of Gujarat University. The team of UGC MMTTC Gujarat University doing very excellent job in organizing such kind of events. It is ranked 15 in the country and number 1 in the state of Gujarat. It is pioneering and creating benchmark by organizing various orientation and refresher courses for different courses via online and physical mode. I did my master in April 2002 from the Sardar Patel University, did my doctorate from Sardar Patel University in May 2006, and title of my thesis is Studies on Novel Coordination Compounds Involving Biological Important Ligands. I was a postdoctoral fellow at University of KwaZulu-Natal, Durban, South Africa, and title of my project was Terbitan Cap Metalloporphyrin Catalyst for Selective Oxidation of Linear Paraffins. I work as a research scientist in pharma industries for 7 years, and I visited USA, Spain, France, UAE for my research work. My main research area is synthesis of different supramolecular platforms and their application as sensor, as liquid crystal material, catalysis, peptide chemistry, and application coordination chemistry and homogeneous catalysis. I published 44 research articles in well-reputed Scopus listed international journals. also written 2 books, and recipients of UGC BSR Research Startup Grant of Rs 10 lakh, and also recipients of International Travel Support Grant from ENRF India to attend ACS Spring in San Diego, California, USA. Four doctorate degree was awarded under my supervision, and 5 research scholars are working in my laboratory right now. Awarded 2 MPhil degree and supervised number of dissertations. Give invited talk in various seminar and conferences, and I am a reviewer of well-reputed international journal. So my main topic, that is basics of supramolecular chemistry. So first of all, we need to understand what is supramolecular chemistry. So the supramolecular chemistry, it is a term given by this gentleman, Jean Marie Lane, and it is a chemistry beyond the molecule, that is chemistry of molecular assemblies using non-covalent bond. And together with C.J. Pedersen, Ronald J. Cram, and Jane Mary Lane received Nobel Prize in 1987 for the great contribution in the field of supramolecular chemistry. In 1967, Pedersen observed that crown ether shows molecular recognition, the first artificial molecule found to do so. Cram established host gas chemistry where the host molecules can accommodate another guest molecule. And in 1978, Lane proposed the term supramolecular chemistry. Together, Pedersen, Cram, and Lane received Nobel Prize in 1987. It is a chemistry beyond the molecule. That means the chemistry of molecular assembly using non-covalent bond. So, according to the Dr. Lane, who invented the term supramolecule, formed by the association of two or more chemical species held together by intermolecular forces, such as hydrogen bonding, pi-pi interaction, hydrophobic interaction, coordination, and so on. So let's see the historical development of supramolecules. So first, in 1891, Villiers synthesized cyclodextrin, and it is a guest-like molecule, so it is used in a host case studies. In 1893, Werner said that electronically saturated molecule can still bind if they have a mutual affinity to form a complex. So this type of molecule which are fully saturated, even though it form a complex, it can bind when the mutual affinity is there. In 1894, the Emil Fischer gives the enzyme substrate interaction lock and key principle. It is about the selectivity and recognition. In 1906, Paul Ulrich said that molecules do not react if they do not bind. So he gave receptor fixation and reaction phenomenon. In 1937, Wolff discovered the gas phase dimer of the carboxylic acid. It is called supermolecules. In 1939, Linus Pauling found that another kind of the chemical bond, that is hydrogen bonding. In 1967, C.J. Pedersen, Jane Mary Lane, and Ronald J. Cram synthesized the different crown ether and cryptons. They are used for the pre-organization, recognition, and templating And 1987, as I already said, they all Jen Maryland, Donald J. Cram, and C.J. Patterson received the Nobel Prize in Chemistry. Recently, in 2016, Stoddard, Sauvage, and Bernard received a Nobel Prize for the constructed a molecular motors by making a molecular rotors blade that continuously spin in the same direction, and in future this molecular machine could be used for the new material sensor and energy storage system. Supramolecular chemistry, it is a interdisciplinary branch. It is connected with different branch and different parts of the chemistry. So we know this atoms, right? Atom combine with the covalent bond and it form a molecules. This molecule join via non-covalent interaction. It is called supramolecule or assembly. And when the supramolecular or assembly have a particular purpose, then and as a function, then this type of material is known as devices, right? So it is the first we can say that's attraction and affinity, then selective binding and fixation and reaction. So molecular recognition is selective binding with a particular purpose. Now self-assemblies. So it is a basic facet of physical world. We know this. Electrons, neutron and other subatomic particles assemble into atoms. Atoms assemble to the give molecule. Molecule reacts with one another to assemble a new molecule, and molecule that may contain hundreds and thousands of such molecules called macromolecules. So macromolecules are of the two types, polymer and macrocyclic compound and naturally occurring substance like steroid and alkaloids. In terms of macromolecules, we can say that all polymers are macromolecules, but all macromolecules are not polymer, because we know that the polymer, it has a different kinds of repeating unit, n number of repeating unit, it is called polymer. Macrocycles are described as a macrostructure having uncharged large ring leading to an intrinsic cavity, means the molecule possesses a hollow space, such as cyclodextrin, crown ether, krypton, sperance, protaxin, catenin, fullerenes, and calixarin. All these molecules fall under the categories of macrocycles. When this macrocycle interact with other molecule by certain non-covalent interactions such as dipole-dipole interaction, ion-dipole interaction, hydrogen bonding, they are termed as supramolecules. Supramolecules in nature. So this particular, we know this more structure, it is a DNA. So naturally occurring DNA is the best known self-assembly structure in the biological system. It exists in double helical form. This is a single helix, this is another single helix. So it exists in double helical form, and these two single strands are held together by a number of hydrogen bonding. Number of hydrogen bonding involving the acidic hydrogen donor. We can see here the acidic hydrogen donor and in and oxygen, that is acceptor. So this kind of hydrogen bonding is available in the naturally occurring DNA. Now we know this and we understand that supramolecule is a molecule assembled via non-covalent interaction. So let's see which type of interaction is available in the supramolecule. So supramolecular interaction, non-covalent interaction represent the energies that hold supramolecular species together. Non-covalent interaction are considerably weaker than the covalent interaction, which can range between 150 to 450 kilojoule per mole for a single bonds. Non-covalent bonds range from 2 kilojoule per mole for dispersion interaction to 300 kilojoule per mole for ion-ion interaction. So, however, when these interactions are used in a cooperative manner, stable supramolecular complex can exist. So all these interactions are very small interactions with a very little energy. But when they combine together, then the synergetic effect give a strong supramolecular complex. The term non-covalent includes a wide range of attraction and repulsion, and which are summarized in table 1. So the supramolecular interaction, different types of supramolecular interaction, that is ion-ion interaction. Its strength is 200 to 300 kilojoule per mole, and we can found this type of interaction in phase transfer catalyst, that is tetrabutylum ammonium chloride. And dipole interaction, 50 to 200 kilojoule per mole, sodium complex of 15 crown 4, 15 crown 5. Dipole interaction, 5 to 50 kilojoule per mole, we found in acetone. Hydrogen bonding 4 to 120, cation piene interaction 5 to 80, potassium ion in benzene, pi interaction 0 to 50, benzene and graphite. Van der Waals forces, that is, it is less than 5 kilojoule per mole, but it is variable, depend on the surface area. We can found in argon and packing in the molecular crystal. Hydrophobic interaction related to the solvent-solvent interaction energy, cyclodextrin inclusion compounds. So let's understand all this interaction one by one. Anion interaction. So it is the strongest interaction, and the it is strongest in interaction, and the bond strength is lies between 200 to 300 kilojoule per mole. They are non-directional in nature, meaning that the interaction can occur in any orientation, and the best example is tetrabutyl ammonium chloride. It is a phase transfer catalyst, an acid-base pair in a particular protein. So it is a ion. This is a positive ion. This is a negative ion. Ion interaction, and it is strong, and its strength ranges between 200 to 300 kilojoule per mole. The second is a ion dipole interaction. They are moderately strong, 50 to 200 kilojoule per mole, and stronger when particularly covalent, 100 to 400 kilojoule per mole. The example is sodium complex of 15 crown 5. It is a structure of 15 crown 5, example of crown ether, and the sodium is inside the cavity, so it is a cation binding host. And metal complex, the ruthenium metal complex with terpyridine, and they are also a ion dipole type of interaction. The next is dipole-dipole interaction. They are relatively weak, 50 to 200 kilojoule per mole. Despite being the weakest directional interaction, dipole-dipole interaction are useful for the bridging species into alignment, as interaction require a specific orientation of both the entities. We can see here the dipole-dipole interaction in acetone. But for this kind of interaction, both the acetone molecule have to arrange in a specific direction, and the dipole moment is 2.91 dBi. Electrostatic interaction are caused by the attraction between oppositely charged species, that is ion and dipoles. Ion and dipole-dipole interaction, however, have orientational dependent aspect, require two entities to be aligned in such a way that the interaction are in optimal direction. Anion interaction are non-directional in nature, meaning that the interaction can occur in any orientation. Electrostatic interaction play an important role in understanding the factors that influence high binding affinities, particularly in the biological system in which there are a large number of recognition processes that involve charge interaction. Indeed, these are often the first interaction between substrate and the enzyme. The next is the hydrogen bonding. So hydrogen bond donor are grouped with hydrogen atom attached to the electronegative atom, such as nitrogen and oxygen, therefore forming a dipole with the hydrogen atom carrying a small positive charge. We can see here this hydrogen is attached with the electronegative nitrogen atom, so the hydrogen carrying a partial positive charge here. Hydrogen bond acceptor are dipoles with electron withdrawing atom by which the positively charged hydrogen atom can interact form a carbonyl moiety. So the carbonyl compound has this electronegative oxygen and which is partially negatively charged. So there is an interaction between the positively charged hydrogen and negatively charged oxygen. So carbonyl accepting the hydrogen bond from a secondary amine donor, and the standard way of expressing donor and acceptor atom. So we have to just remove the particular hetero atom and we say this donor and this is the acceptor. The strength of hydrogen bond can vary different between various systems, and it is not necessarily with Bronsted acidity and the proton donor. It depends on type of electronegative atom to which the hydrogen atom is attached and the geometry that the hydrogen bond adopt in the structure. Typically, the strength range from 4 to 120 kJ per mole, with the vast majority under the 60 kJ per mole, and scale of hydrogen bond acidity, basicity have been developed. These are the different types of the hydrogen bonding geometries. That is, it is a linear kind of hydrogen bonding. This is a band type of hydrogen bonding. This is a donor bifurcated type of hydrogen bonding. This is acceptor bifurcated type of hydrogen bonding. It is a trifurcated hydrogen bonding, and this is a three center bifurcated. Here 1, 2 and 3 acceptor are there. So three center bifurcated type of hydrogen bonding. The most important non-covalent interaction in the design of supramolecule and high degree of directionality, it represents a special kind of dipole-dipole interaction between proton donor and proton acceptor. They are highly directional nature of hydrogen bonds interaction together with a specific alignment of hydrogen bond donor and acceptor has proved to be fruitful asset for the design of supramolecular system. So majority of supramolecular compound possess this type of hydrogen bonding type of the interaction. So the interaction property donor hydrogen acceptor, it is a mainly covalent type, mainly then it is a strong, mainly electrostatic, then it is a moderate, and electrostatic it is a weak, right? Bond energy ranges between 60 to 120, 16 to 60 and less than 12 kilojoule per mole. Bond length donor hydrogen to acceptor is 1.2 to 1.5 in a covalent type of bonding, strong 1.5 to 2.2 moderate hydrogen bonding, and 2.2 to 3.3 angstrom. It is a weak kind of hydrogen bonding. Donor to acceptor bond strength is 2.2 to 2.5, 2.5 to 3.2 for a moderate, and 3.2 to 4 for a weak donor to acceptor hydrogen bonding. Bond angle ranges between 90 to 180 degree. An example, these are the different example of the different kinds of strong, moderate and weak hydrogen bonding. Next is a pi interaction. So there are two main type of pi interaction are found in the supramolecular system, that is cation pi interaction and pi interaction. The cation pi interaction are well known in the field of organometallic chemistry, right? This is an example of organometallic chemistry where the olefinic groups are, these are the olefinic groups, right? This is the olefinic groups are bound to the transition metal, are bound to this type of transition metal. For example, ferrocene and J salt, but these are not regarded as a non-covalent interaction. Cation pi interaction relatively weak. Alkaline and alkaline earth metal also form interaction with double bond system. For example, the interaction of potassium ion with benzene has a similar energy of K plus as water interaction. So this is a benzene, right? And this is a potassium ion. So potassium ion attract with this benzene. Why? Because the benzene possesses a pi interaction. We know this. It is an electron cloud moving around the ring, and the interaction energy is 80 kilojoule per mole in gas phase. Pi-pi interaction, they are weak and strength is 5 to 50 kilojoule per mole. There are two types of pi-pi interaction, phase to phase and edge to phase. We can see here the phase to phase interaction, and this is the edge to phase interaction. This is the top and side view of the layer structure of the graphite. They held together by phase to phase interaction. The layer structure of graphite is held together by weak face to face interaction, and therefore they feel slippery, and it is because of the slippage between the layers the graphite can be used as a lubricant. Interaction involved pi system can be found in nature. Example is weak face to face interaction between base pair along the length of double helix are responsible for the shape of DNA. The next in the list is van der Waals interaction. It is also called mutually induced dipoles. So these are dispersion effect that comprise two components, namely London interaction and exchange and repulsion interaction. They are very weak, 2 to 20 kilojoule per mole. Van der Waals interaction arise from fluctuation of the electron distribution between species that are near to one another. London interaction between two argon atoms, the shift of the electron cloud. See, this is a nucleus, and mostly we found the nucleus in the center, but the shift of this electron cloud and the nucleus on another direction. So nucleus produce a interstitious dipole that attracts each other. So this nucleus moves on one side, so it has a positive charge. Electron cloud move in opposite side, it is a negative charge, and there is an interaction between these two different argon atom, and it is called London interaction. Hydrophobic effect. Hydrophobic effect arise from the exclusion of non-polar group or molecule from the aqueous solution. This situation is more energetically favorable because water molecule interact with themselves or with other polar group or molecule preferentially. The two organic molecule creating a hole with an aqueous phase, giving rise to the entropic hydrophobic effect. One hole is more stable than two. So this is the example of hydrophobic effect. This is the water molecule, and this is another the organic molecule. So this organic molecule take a place between the different kinds of water molecule. The supramolecular chemistry mainly divided into two broad categories, that is self-assemblies and host gas chemistry. So molecular chemistry, which is a chemistry of the covalent bond, and supramolecular chemistry, it is a chemistry of the non-covalent interaction. So two different small molecule, they combine via covalent synthesis and form a host, means it is a receptor, and this kind of receptor as a guest, and with a non-covalent synthesis they form a supramolecules, right? So this host is also called receptor and molecular building blocks. Generation of supramolecule. So now I'm going to discuss about the various supramolecular platform. Generation of supramolecule, which is defined as the chemistry of the non-covalent interaction or as the chemistry of the molecular assemblies. It is classified on their time scale, that is first generation cyclodextrin, second generation crown ether, third generation calixarine. So we start with the first generation of supramolecule, cyclodextrin. Cyclodextrin are synthetic substance, this is the structure, obtained from enzymatic degradation of the one of the most essential polysaccharides, that is starch. Cyclodextrin were originally observed by Villiers in 1891 using Bacillus amylobacteria as enzyme. So this starch is degraded by this Bacillus amylobacteria enzyme and form this type of molecule. This is the top view of the molecular model, and this is the chemical structure. We can see here the glucopyranoside unit is joined by 1,4-glycosidic bond, and this particular structure is known as beta cyclodextrin. Cyclodextrin contain 6 it is called alpha, 7 it is called beta, and 8 it is called gamma. D-glucopyranose unit linked by this type of 1 and 4 glycosidic bond. The family of cyclodextrin include 5 repeating units to 12 member units. On the industrial scale, beta-cyclodextrin are produced by enzyme cyclodextrin glucanotransferase. The industrial importance of cyclodextrin was identified in 1948 when the crystal structure of gamma cyclodextrin was solved by Fredenberg and Kramer. The structure revealed the cyclic nature of the compound and their potential to include guest molecules. The narrow lower rim, this is a narrow lower rim, right? The narrow lower rim which bristles with two primary hydroxyl group per dextrin repeat unit. Properties of cyclodextrin. Their outward pointing hydroxyl group. Their outward pointing hydroxyl group makes cyclodextrin water soluble with retaining a hydrophobic central cavities. The aqueous solubility of beta cyclodextrin at room temperature is 18 gram per liter, which is much lower than alpha and gamma cyclodextrin, which is 145 and 230 gram per liter respectively. All the cyclodextrin are 7.9 angstrom in depth. So the height of the torus is 7.9 angstrom. However, the outer diameter and the cavity size increases with the number of cyclodextrin unit. This gives alpha cyclodextrin an overall diameter of 14.6 angstrom and the cavity size around 5 angstrom. Beta cyclodextrin 15.4 angstrom and 6.5 angstrom cavity size, and gamma cyclodextrin outer diameter is 17.5 angstrom and the cavity size is 8 angstrom. So these are the different structure. Alpha cyclodextrin with 6 repeating units, this type of repeating units, the N is 6 here, N is 7, it is called beta cyclodextrin, N is 8, it is called gamma cyclodextrin. So the height of torus, all the alpha, beta and gamma has the same height, that is 7.9 angstrom, but the cavity diameter is different. It is vary in alpha, beta and gamma cyclodextrin. The hydroxyl group on upper and lower rim of the cyclodextrin are good site for the substitution. So this molecule possesses one particular glucopyranose unit contain 1, 2 and 3 hydroxyl group. So it is good site for the substitution. However, due to the chiral nature of the parent compound, large number of repeating units, the derivatization of the cyclodextrin is a complicated matter. The crystal structure shows that cyclodextrin in complex adopt round structure with all glucopyranose unit in a 4C1 chair conformation. Apart from this naturally occurring cyclodextrin, many cyclodextrin derivatives synthesized in the laboratory. These derivatives are produced by amination, esterification, etherification of primary and secondary hydroxyl group of the cyclodextrin. Depending on the substituent, the solubility of cyclodextrin varies different from that parent cyclodextrin. Virtually all the derivatives have charged hydrophobic cavity volume, and also their modification can improve solubility stability against light or oxygen and help to control the chemical activity of the guest molecule. The synthesis of uniform cyclodextrin derivatives require regioselective reagents, optimization of the reaction condition, and a good separation procedure. The most frequently studied reaction is the electrophilic attack at the hydroxyl group, the formation of ether and ester by the alkyl halides, epoxides, acyl derivatives, isocyanates, and by inorganic acid derivatives such as sulfonic acid chloride. Cleavage of COH bond has also been studied frequently, involving a nucleophilic attack by compound like azides, halide ions, thiols, thiourea, and amines. This requires activation of oxygen atom by an electron withdrawing group. Because of their ability to link covalently or non-covalently, especially to other cyclodextrin, cyclodextrin can be used as a building blocks for the construction of supramolecular complex. So this is a modification of cyclodextrin. If we perform a grafting, then we can get an amphiphilic cyclodextrin. If it is self-assembled, then we can get a self-assembled structure. When it form a cross-linking or order assembly, then we get a cyclodextrin molecular imprints. When it is polymerized, we get nanosponge. It is just covalent conjunction and cross-linking. We get a cyclodextrin complex and nanoreservoirs, right? And multi Miller vesicles. So these are the, we can just do a modification and we get a different kinds of cyclodextrin type of compound. Biological activities of cyclodextrin, it is extremely biocompatible. They are unable to significantly permanent biological membrane and are not absorbed by the gastrointestinal tract, yet do not include a response from the body immune system. The test on rat indicate the LD50 values for the most toxic parent compound, that is beta cyclodextrin, are greater than 5 gram per kg of the body weight when administered orally and 0.5 gram per kg of body weight when administered intravenously. The low level of toxicity coupled to the cyclodextrin ability to form an inclusion complex make them ideal excipients in pharmaceutical formulation. The properties of cyclodextrin. Alpha, we just discussed the two main category, alpha and beta cyclodextrin. Number of glucopyranose units 6 and 7 in beta. Molecular weight 972 and 1135. Solubility in water at 25 degrees Celsius temperature 14.5 for alpha cyclodextrin and just 1.85 gram for beta cyclodextrin. Outer diameter 14.6 and 15.4 respectively. Cavity diameter 4.7 to 5.3 angstrom for alpha cyclodextrin and 6.0 to 6.5 angstrom for beta cyclodextrin. Height of torus, it is 7.9 for alpha cyclodextrin and 7.9 for beta cyclodextrin. And cavity volume 174 angstrom and 262 angstrom. Cyclodextrin have a wide range of application. It starts from cosmetic and toiletries, catalysis, biotechnology, textile and paper industries, formulation of detergents, glue and adhesives, polymer industries, pharmacy and medicine, food industries, and inclusion complex. So these are the example of marketed products containing cyclodextrin derivatives, and these all are the marketed drug, and this is a cyclodextrin inclusion complex mostly prepared for their good solubility, right? Alpha cyclodextrin, beta cyclodextrin, 2 hydroxy propyl beta cyclodextrin, methylated beta cyclodextrin, sulfobutyl ether beta cyclodextrin, and 2 hydroxy propyl gamma cyclodextrin. These are the excipients, means, and these are the drugs, and it is from a different kinds of inclusion complex. The second generation in the supramolecules, it is a crown ether. So it is synthesized by this gentleman C.J. Patterson in 1967, and he awarded the Nobel Prize in chemistry without having a PhD degree. Crown ether is generic name given to macrocyclic polyether containing ethylene bridge. See, this is oxygen, oxygen, and this is a ethylene bridge, CH2, CH2, separating two electronegative oxygen atoms. So these two electronegative oxygen atoms separated by this ethylene bridge. The discovery of macrocyclic polyether is interesting in recent development of separation chemistry. They typically contain central electron rich hydrophilic cavity. This is a hydrophilic cavity with diameter varying from 1.2 to 6.0 angstrom. This is the structure of 18 crown 6. So 1, 2, 3, 4, 5, 6. 6 is heteroatom and total number of molecules is 18, so it is called 18 crown 6. The discovery of cyclodextrin led to enormous advances in the chemistry. The hydrophobic cavity is ring with electronegative binding heteroatoms such as oxygen, nitrogen, sulfur, which in turn are surrounded by a collar of CH2 group, forming a framework which is flexible and exhibits hydrophobic behavior. The hydrophobic exterior allows them to solubilize ionic substance into non-aqueous solution and in membrane media. How it is discovered? The discovery of first crown ether. C.J. Pedersen was working in an industrial chemistry lab at DuPont. A project was initiated in 1961 by him to find new vanadium containing catalyst for the polymerization of olefins. Pedersen decided to study the effect of uni and multidentate phenolic ligand on the catalytic property of the vanadidyl group. Quincudentate ligand selected was bis 2O hydroxy orthohydroxyphenoxy ethyl ether, and the synthesis was begun according to the route outlined in the scheme A. This is the scheme A. During the synthesis in ligand from catechol, a small quantities of byproduct in the form of silky crystal was obtained, which showed strange solubility behavior, which led to further spectroscopic studies and resulted in the discovery of the very fine compound, that is the first crown ether, which was named as dibenzo 18 crown 6. Since the large number of crown ether was then synthesized, so this is a synthetic, it starts with the catechol, this is a protein protecting group, and they form a compound A. Compound A reacts with this the second material in basic condition, and from this is a targeted ligand for the vanadidyl compound, and this is a byproduct, and this byproduct is known as the dibenzo 18 crown 6. These are the different crown ether compound: 12 crown 4, 15 crown 5, 18 crown 6. Diaza, 2 oxygen atom is replaced by the nitrogen atom, so it is called diaza 18 crown 6. And in place of the CH2 polar group, here the 2 aromatic ring is there, benzene ring is there, so it is called dibenzo 18 crown 6. Classification of crown ether. The organic neutral ligands are classified into 2 groups, that is podents, right? Podents, coherents, and cryptants. Coherents are their open chain compound. This is an open chain compound and are characterized by lacking ring and bridge structure. Coherents, they are cyclic compound. These are the cyclic compound. Coherents containing oxygen as a donor atom are called crown ether. Those containing oxygen and nitrogen as donor atom are also called as the crown ether. And other containing oxygen and sulfur, they are called a thia crown ether. These are the structure of cryptons. They are macropolycyclic polyethers. So 2 or 3 ring is there, are classified into bicyclic, tricyclic, and tetracyclic. Application of crown ether: membrane transport, chromo and fluoroionophore, extractive separation analysis, phase transfer catalysis, ion chromatography, isotope separation, ion selective electrodes, and molecular recognition. Next in the list is the third generation of supramolecule, that is calixarin. The term calixarin was given by C.D. Guts in 1978. Calixarin is derived from the Greek word means calyx, that is vase or concept. The molecule is just a cup or concept molecule. 2 different zones can be distinguished, the lower rim and the upper rim. This is called the upper rim and this is called the lower rim. This is the structure of the calixarin. Lower ring, it is a phenoxyl hydroxyl group. It is called phenoxyl hydroxyl group. And upper ring, the para position of the phenol, that is tertiary butyl group. And this is the another structure. It is called the different kinds of cyclodextrin. This is the resorption 4 arene. So this is the calyx 4 arene, calyx 6 arene, calyx 8 arene, and this is the molecular model with C.D. Guts and his wife Alice. Calixarin may be divided into into following two broad classes, that is heterocalixarine and heteracalixarine. Heterocalixarine, when the organic moiety pyrrole, right, thiophene and furan, they are called heterocalixarine. It is called calyx pyrrole, calyx thiophene and calyx furan. Tetracalixarine, when the methylene junction involve element like oxygen, nitrogen and sulfur, they are called heterocalixarine. So in the bridge sulfur is there, it is called thiacalix. In the bridge oxygen is there, it is called oxacalixarine. Calixarine has different conformation, right? So the rotation of this phenolic moiety via this CH2 bridge group, it form a cone, partial cone, 1,2 alternate and 1,3 alternate type of different conformation for the calixarine, and it is firstly synthesized by the Hayes and Hunter's stepwise synthesis to get the calyx 4 arene, and it start with the paracresol, right, paracresol, and then it is protected, and after then it is the reactive group is deprotected, and we form a final compound calyx 4 arene. Mostly this type of compound is formed via acid and base catalyzed reaction. Synthesis of calixarine derivatives. So instead of the simple phenolic moiety, the naphthol is there. So naphthol is a mixture containing 16% of calyx 4 naphthalene along with two other isomer yield 9.6 and 5%. So the different orientation of the hydroxyl group is different, and we get a different isomer. Another kind of calixarine molecule, it is a tetramethoxyresorption for arene. So it is a preparation of enantiochemically pure tetramethoxyresorption for arene. Trimethoxyphenol gives this type of racemic compound with OH and OCA3 group in different position, and when it react with the chiral compound, right, phenyl ethyl isocyanates in presence of dibutyl dilaurate, we get a we can separate out both this racemic compound, both the isomer PSS and MRS, and after that we hydrolyze this protecting chiral group, and we get a anisomerically pure compound. Another compound is 2,6-dihydroxyacetophenone for arene. It is a base catalyzed synthesis. It starts with the 2-hydroxyacetophenone. It reacts with various aldehyde in presence of base and form a 2,6-dihydroxyacetophenone for arene. This type of compound cannot be cyclized in an acidic condition because it possesses the electron withdrawing group at the second position. So it cyclizes only in a basic condition. Metallocyclophane containing heteroatoms such as oxygen, nitrogen and sulfur groups are bridging moiety, also qualifying as members of calixarine family. In 1966, Sommer and Stebbs synthesized first oxacalixarine macrocycle. So it started with resorcinol and went to dichloro 2,4-dinitrobenzene. In basic condition, it gives a oxacalixarine, and this is another example of thiacalixarine. In my postdoctoral studies, I worked on resorcin for arene cap metalloporphyrin compound, and which is used for the oxidation of linear paraffins. So the synthesis starts with the resorcinol, and it forms a resorcin for arene. Then the bromo group is introduced in this upper rim, and this bromo is now converted into hydroxyl group. This hydroxyl group combined with this bromoalkyloxybenzaldehyde, and this aldehyde group is react with pyrrole and form this type of porphyrin ring. So this is the compound of resorcin for arene cap porphyrin, and this porphyrin group moiety is metallated with the compound, so it is generate resorcin for arene cap metalloporphyrin type of compound. This is the structure of resorcin for arene cap metalloporphyrin. That metal compound is nickel in the cavity of the porphyrin, and this specific compound is used for the oxidation purpose, oxidation of the linear paraffin. These are the other type of compound, that is cyclotrivalentylene CTV with cavity size, right? Pilararine, right? This is a pyrogallurine. Pyrogallurine has a 3 hydroxyl group, so we can substitute any functional group on 12 different sites, right? This is the crystal structure of another pyrogallurine moiety, and this is a pilararine. This is a side view and top view, and we can see here this type of host molecule can accommodate a guest molecule in the cavity. We see here the dichloromethane is there. Functionalization of calixarine can be done on this hydroxyl group or in the upper rim in this the position of this position, or we can functionalize this hydroxyl group. The resorcination functionalization can be done at the upper rim and all these 8 hydroxyl group. Calyx pyrrole can be functionalized at this R position and the pyrrole unit carbon. Thiacalixarin can be functionalized as the upper rim aromatic carbon and the sulfur and the hydroxyl group. So all these molecules different functionalities. Oxacalase can functionalize the hydroxyl group and the aromatic ring. So the application of supramolecule. Supramolecule has a wide range of application, right? It starts with a liquid crystal, bioimaging, drug and gene delivery, therapeutic agents, and sensing of amino acid and metal, explosive chemical warfare agents, right? It is also used in a solar cell application, display devices, OLED, multiple targeting, multimodal imaging, right? Combinational therapies, controlled release, multiple targeting, bioavailability, specificity. So we can see here the supramolecule type of compound has a various application, right? Now I'm going to highlight the research work carried out in my laboratory. So the supramolecule is used as fluorescent recognition, drug delivery, targeted drug delivery system, fluorescent material, and artificial enzyme. It is also used in a liquid crystalline material, catalysis, sensing application of amino acid, cation, organic molecule, and chemical warfare agents. Analytical technique for molecular separation. It is also used for drug delivery, and it is used for the fluorescent chemosensor that can sense any kind of toxic material, chemical warfare agent, pesticide, fungicides, uh, metal salts, explosive, anything. You can sense anything by this type of compound. This is a molecule resorcinfonerine microbe assisted synthesis, and we get this compound, and it is a biological important liquid crystal. When it assemble, it gives a liquid crystal. It is published in Chemistry Select. This is another kind of molecule, right? Resorcinfonerine, but it is a lower rim functionalized. We reported first time this lower rim functionalized molecular crystals, right? That is published in Journal of Molecular Structure. This is a self-assembled structure of this type of different supramolecules, and it is published in molecular crystal. It is also molecular crystal and liquid crystal. It is also used in a liquid crystal material. It shows a hexagonal columnar texture pattern. Another kind of supramolecules, which is also lower functionalized, right? And we synthesize 8 different material. It is based on the calyx core compound. It is published in Journal of Molecular Structure. It is used in a bioimaging application. Cyclotrivalentylene is converted to cyclotriglycine, and it is used as a self-assemble behavior, light emitting properties, right, and electron optical properties. This is a material, right? It is a resorcinfonerine type of derivatives, and it is used for the ion sensing. We can sense the ion in real sample also. The nematic phase liquid crystal material can be obtained by pillar 5 wherein, right, 4 supramolecular liquid crystal was synthesized by this parent pillar 5 wherein it is published in Journal of Molecular Liquids. The compound that is resorcinol reacts with this type of molecule and in acidic condition form a target compound, and this target compound has a fluorescence behavior, right, and it is a multi-layer liquid crystal material and with high thermal stabilities. So importance of supramolecule: due to the great variety of ways for their further functionalization. Why these supramolecule are important? Because we can functionalize this molecule all the different platform: cyclodextrin, crown ether, and calixarin. They can be functionalized in different ways. Versatile complexing properties. We can make a different types of complex. They have a different conformational flexibilities. You can make a different conformation because the ring is flexible, the bridge which is flexible, easy to synthesize because mostly it is a single step or two-step procedure, commercially available. All the reagent, all the starting materials are commercially available, and the procedure are economically viable also because they produce a less byproduct, right, and less effluents. Eco-friendly synthesis, right, and all the starting material reagents are very cheap, means available in affordable cost. They have found to function as all the supramolecule can be used for the specific function such as macrocyclic receptor, dendrimer in biological system, nanocapsule, nanoparticles, nanosponge, optical chemosensor, supramolecular tecton, host molecules, component in liquid crystal, photoresist material, selective membrane, surface reforming agents, HPLC stationary phase as a ligand for metal organic frameworks, key starting material for molecular machines, and ion channel mimics and metal ion extraction agents. So, the supramolecule, as per your expertise and convenience, functionalize them with those functional group with which you are comfortable with and you are already working with, and allow them to function as per your desired function. I am sure that they will function better than your expectation. You will get उम्मीद से ज़्यादा. The reason behind that, the more number of functional group present on the parent compound. Functional group may be circularly arranged and it is pre-organized, may acquire different conformational cone or partial cone, or maybe sometimes 1,3 alternate and 1,2 alternate. Enhance reduce binding due to the hydrogen bonding. Hydrophobic in nature, so it is influence binding due to interesting cavity, hollow space, and possibility of hydrogen bonding in these supramolecules may allow this compound to behave as ditropic or tritropic receptor. After functionalization, they may form a superstructure by self-assembly. So special notes of this talk, right? Coffee never knew it would taste so nice and sweet. Before, it made milk and sugar. So we are good, we are best as individual, but become better when we meet and blend with the right people. So take home messages, collaborate with different disciplines, and now the National Education Policy 2020 also emphasize the multi or interdisciplinary research. So collaborate with the different people. So I would like to acknowledge my past research scholar and the present research scholar, the coordinator of the course, Dr. Dilip Vasawa, and Professor Joshi, the Director, UGC MMTTC Gujarat University. And thank you for listening me. And thank you so much for giving me an opportunity to present my views on the basics of supramolecular chemistry. Thank you.